Well, thank you. Thanks. Welcome. So what I want to do is give you guys an overview of speech synthesis, what's involved if you're looking at speech synthesizer and you were to open up and look inside what's in there. But before I start, how many of you have been inside of a speech synthesizer? Who's seen inside? Can you tell me a little bit about what your background is or your familiarity with speech synthesis?
I played a little bit with Festival.
Uh-huh.
And I now work trying to play with HDS.
Uh-huh.
And Festival.
Okay. Okay, so you'll recognize a lot of what I'm saying, and it might put some of the wider context around that for you. Anybody else? Cool. Okay. So first of all, they told me never start with the caveats, but I'm going to. My hard drive crashed, so I'm going to be using the whiteboard instead of my slides. I'm sorry about that. Bear with me. So we'll close that so it doesn't get distracting, and hope that it resyncs when it wakes up. There we go. Whoa. All right. Don't get distracted by it. Speech synthesis touches about every layer of artificial intelligence, linguistics, and signal processing. There's this long-standing kind of friendly rivalry and banter between people who do research in speech recognition and people who do research in speech synthesis. Morgan, I'm sure you're familiar with this, that each says, well, I'm working on the really hard stuff. And if you go to most speech recognition researchers and say, why aren't you working on speech synthesis? They'll say, because speech synthesis is a solved problem. And then if you say, and why are you using recordings of human speech in your demos rather than speech synthesis? They'll say, because speech synthesis doesn't sound natural enough. So to do speech synthesis, I'd like to take you through the major boxes that will be in the process. And the first one of these is text normalization. Can I write up here somewhere? Tell me if I write up here if my writing's too small. Text normalization is I can do this one. Taking the text that's coming in and trying to figure out what should the words be for this text. And for something like the cat sat on the mat, it's pretty straightforward, but most sentences aren't like that. For example, if the synthesizer sees this, what would be a reasonable way of saying that? I'd figure 36, right? If it sees this, then it should maybe say 1.36. If it sees a dollar sign in front, then it should not be dollar sign 1.36, it should be $1.36. Unless there's something like this after it, in which case it should not be $1.36 billion, but rather $1.36 billion. So it needs to do some forward looking, then some back looking, then figure out that this should be a plural. The point is that the string of orthographic tokens that comes in does not necessarily, in fact, often does not map onto the string of words, even linearly. And there's a lot of ambiguity in there. The good thing about this case is that it's tricky and complicated, but it's not that ambiguous. There are some texts where you might want to say $1.36 billion. If you thought about it, maybe as homework tonight over a beer, see if you can think of a sentence where that would not be $1.36 billion. You'll be able to think of one. One way would be Google it. I bet you find one. Okay, so another subset of cases for text normalization that are rather more difficult. Things like this. That could be March the 1st, or if you were from Australia like I am, actually if you're from Australia like me, that could be would be March the 1st. See, I'd lose my intuitions. I guess for most people in the United States it would be January the 3rd, but it's actually 1/3. Well, what it is depends on the context. In many contexts, people use this in, for example, Associated Press news to mean 1 out of 3 times. So if you transcribe that as, or speak it as 1/3 times, speech synthesis is like magic in the following sense. When you get it right, nobody sees a thing. Nobody notices. But when you get it wrong, it's glaring. So people will listen to your synthesizer, say a third time, and think, stupid synthesizer. God, couldn't they even get something as simple as that right? So There are a number of approaches to text normalization, and they all boil down to needing a lot of prior knowledge, which is tedious, laborious, and needs to be entered by hand by people who understand the nature of the text normalization process. There are a number of formalisms for doing this, and the interesting work is in generalizing from the cases that have been entered to be able to recognize cases that have not been entered. So you could cover all the cases that I just described now. Well, the money cases you could describe with a few regular expressions. Unless you're reading out a text that has a quote of some money amount from a different currency or in a different language. And so it would be nice if you could have a system where you could specify how money is to be spoken in a few currencies and specify the signs for other currencies, and then have the synthesizer, well, the text processor itself, be able to learn how to generalize. And the methods that I've seen that try to do that statistically have not been that exciting. They will learn some cases, but will mess up on others. So I don't yet see much that's exciting in the area of text normalization that's statistically driven yet. But it is an interesting case for machine learning, ways to learn from known examples to recognize other examples. We'll move back to a subset of those later when we talk about named entity recognition. But play a mind game with me. Suppose you could write a system that could take 99% of all the texts that people would put to it and do correct text normalization, expand the appropriate abbreviations, deal with cases where strings of symbols need to be expanded into sets of words, even if it meant changing the order. Are we done? Not at all. Because once you've done text normalization, then you need to figure out how to say the word string that you've got. And to recognize that, you need to know more about the words. For example, here's my eraser here. Let's think of some good examples. All right. First of all, there's word pronunciation. The pronunciation of most, well, not most, many words is ambiguous. That is, the same word could be pronounced different ways depending on its part of speech or its word sense. Let's take the part of speech case first. You all know, I'm sure, cases like this. I object to that object. The object of this exercise is not the object. There are maybe tens of thousands of these in English. Let's see. The ATE words. I have hand-fixed probably a couple of thousand of these, and I always have trouble remembering any good examples because they're in my slides. Adjudicate. No. So the problem here is a verb with an eight when the AT is pronounced as 8, or a noun when it's pronounced as an ut. You think of different examples, adjudicate versus an affricate. But there are lots of cases where, can anybody think of one? Jeez. Perfect, thank you. Oops. So there could be 8 or, I don't know, let's do a schwa. We'll talk about that more. Schwa there. So you need to know it's part of speech. There's many cases of those. One large subset is names. There are a lot of names that can also be pronounced as words and should be pronounced differently. Begin, demos, versus begin, demos. So a part of the word processing, once you've got the words, is to figure out what part of speech they are. Oh, thank you. I didn't know that you were awake. What part of speech they are, and whether they are a name or not. It's not exactly part of speech because a name functions as a noun. So you need to do part of speech tagging. That begs the question of what's the tag set? There are about 9 part of speech tags that are agreed upon by different schools of parsing of English. And if you look up the Wikipedia page, you'll find that list. Noun, it's what we all learned in school, right? Noun, verb, adverb, adjective, determiner. Turns out that that's way too impoverished to know how to say them. Partly because of the pronunciation of the words, and partly because of the contribution they have to phrasing, to chunking. So let me give you some examples. This keeps speech synthesis researchers up at night. How should that be pronounced? Tick, 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 tick. That, yeah, I would think so. But in a sentence like, that's true in a sentence like, I know that. But if I say, oops. Yes. Case like, I know that that is difficult. Here, you can have a schwa. Actually, it's a barred I. It's a raised schwa. Here, you it would be wrong to say, I know that. Right, I could say, I know that, but I can't say, I know that. I could not say, I know that that is an example, or I know that that is difficult. So you need to know the role of each instance of that. This case is trivially easy because I put quotes around. But in a sentence like, he said that that was not his fault. Much harder. And being able to determine which part of speech that has, whether it's a pronoun or a conjunction, is difficult. Once you know that it's not, if it's a conjunction, then it's reduced. Right? I know, and that is different, 2 sub-sentences joined by the conjunction here. So in the case of a conjunction, it gets reduced. That's a general principle in English, that words that can be conjunctions, but sometimes aren't, when they are conjunctions, are usually spoken with a reduced vowel. There's a third case of it being a relative pronoun. I didn't know that. There's actually a relative pronoun there. Like I didn't know him. And then there are cases, actually simpler cases if they're helped by punctuation, although they often aren't, of use versus mention. Right? Here we're mentioning the word that rather than using it. Another pervasive problem with part of speech is what part of speech to actually apply for many of the things that come up in real text. Like, what is the part of speech of that? Is it a personal pronoun? Well, no, because it's not an I. Is it a verb? Well, not exactly, because it can function in a sentence by itself. So it seems to me that our notion of part of speech needs to be expanded to what part of speech does this unit look like when we're looking from the left versus what part of speech does it look like when we're looking from the right. And there's a large set of those in English. Couldn't have, Okay, we could go on. Here's a nice one. Gonna, woulda, shoulda, kinda. Right. Gonna arguably is going to. Kinda is grammatically quite different because, oops, kinda, because you can get a prosodic boundary in the middle of the word. Because it's an of, kind of something, right? So the very notion of part of speech is more complicated than simply assigning labels to spatially separated orthographic tokens. There are a number of approaches that have been taken to part of speech. The most successful ones in this case are statistical. Before statistical approaches were taken, the computational linguistics community believed that in order to figure out part of speech, you had to do a full parse. Because if you have a sentence and you can generate the whole parse tree, you can resolve ambiguities of the kinds I've been talking about by referring to the overall parse tree. Trouble is, they couldn't actually make it work very well. And then some early work, one of the first researchers, not the first, but one of the early ones was Ken Church, took a more statistical approach where they take a corpus that was transcribed with parts of speech. He used the Brown corpus. Anybody not know the Brown corpus? Who does not know the Brown corpus? You'll hear about this a lot. It's a corpus that largely got us going in statistical processing of text, right? Yeah. So some psychologists, heaven help us. I can say that because I'm a psychologist. Psychologists got a 1 million word corpus typed on typewriters by hand and hand labeled the part of speech of every word and calculated word frequencies from this corpus. What they did that was interesting was reaction time tests. Shut up. Reaction time tests are you present a person, sit a person in front of a screen, flash up a word to them, and, well, a letter string, and they have to press a button, button A if it's a real word, button B if it's not a word. Right, it's as simple, is this a word? And you measure how long they take to do it. And it turns out that one of their big discoveries that got us thinking about how to process text was the time it takes to decide whether a letter string is a word or not correlates with the log of the frequency of that word in the language. We're quicker to recognize a letter string of a given length as being a word if it's more common. Not only are we quicker if it's more common, you can actually predict the word's frequency from how long people take on average to make a decision about whether it's a word or not. For all words, except for function words are all roughly equally fast. But that's kind of interesting. Okay, so this corpus became available and was mainly used for looking at approaches to understanding how the mind processes language. But then some computational linguists, Ken Church being one of them, thought about assignment of part of speech and thought maybe we could take a statistical approach to that. And so took the Brown corpus and calculated for each word the distribution of possible parts of speech that could occur after it. How often is the followed by a noun? How often is the followed by a verb? It turns out not very often, right? And so by making up those pairs, probabilistic pairs, you could then take any string of words and find the most likely sequence of parts of speech to minimize the cost of that path through the matrix of all possible parts of speech. Is that being clear? Yeah, okay. And so that was pairs. Actually, Ken Church did it with triplets of part of speech on the left and part of speech on the right. There is a problem there of what do you do with triplets that you've never seen before? And so we came up with a very simple approach to that. When you're doing your initial counts from your corpus, you calculate all the combinations you haven't seen before and just add one. In fact, you add one to all counts, and then that covers them. So simple. But there's a good mathematical justification for that it's roughly right. Morgan, I think there's been some more recent work to show that it's not quite right. Yeah, yeah. Okay, so work from there has grown to hidden Markov models, visible Markov models for predicting part of speech. I like the statistical approaches, and here I was intrigued by Ken Church's justification for them. He said, yes, there's no linguistic representation here, no representation of linguistic knowledge of phrasal structure or transformational grammar. But, he said, look at the psychological literature. If you're designing a psycholinguistics experiment, such as a reaction time experiment, you have to be careful to control for extraneous variables such as word frequency. If I'm doing an experiment to look at, do people process sentences about me quicker than they process sentences about a rock, then I have to make up sets of sentences, but I have to make sure I equate for word frequency in those sentences. In fact, the reason you have to equate for things like frequency is because the effects of frequency are much larger than the effects of the experimental variables that people are trying to measure in most psycholinguistics reaction time experiments. Maybe frequency is important. And that was his argument. And I thought, yeah. All these things we carefully factor out to ignore, maybe they're the bigger things. So we need to get part of speech. One reason is to figure out the word pronunciation. Another reason for getting part of speech is to do phrasal chunking. If you have a synthesizer that can do all the text normalization correctly and all of the recognition of names versus non-names correctly and part of speech assignment correctly and comes up with some reasonable way of dealing with the large number of cases where simple part of speech just doesn't apply, you're still not done. Because when we speak, we don't just open our mouths and utter an undifferentiated string of words all placed together into a long string with no internal structure. Rather, we chunk our speech into phrases, and we chunk those phrases into larger organizational units, and we signal that structure to our listeners by the way we say them. So if we're going to synthesize speech, we better model that. One subset of cases that has not received much attention in the synthesis literature until recently, and is really important if you make a real commercial synthesizer, is named entity detection. By named entities, we mean things like people's names, organizations' names, locations, like London, England. And it turns out if you're taking large amounts of text around, technical terms, like part of speech, and entertainment terms, that is movie titles, song titles, album titles, and heaven help us, artist names. So one of the reasons to do named entity detection is that if you see a string of words that you recognize as being a named entity, a reference to something, you need to speak it in such a way that it gets separated from the surrounding text. See if I can give you an example. Is this writing too small? Okay. This kind of thing often comes up. If you put this through any kind of text processor that tries to figure out how to say this sentence, know that this is the title of a song, and it was something like, I added singing in the rain to my collection, right? Which is, well, if I say it like that and you're looking at the transcript, you can understand my words. If it occurs in the process of hearing a whole lot of text that you haven't understood, it'll trip you up. So what we need to do is the speech equivalent of that. which people sometimes do in their text, but not always. And this happens for city names, like Forest Hills, and people's names, artist names, and so on. So named entity detection is one case of... Oh, thank you. Should I shut him up? No, actually, I keep it going so I keep on track. Named entity detection is an area of text processing that is important for speech synthesis and is difficult and has largely not been addressed in the literature. So we don't have, I think, very good approaches to these in the speech synthesis field, which is interesting because in the text retrieval field, people have dealt with this in a lot more detail. The kinds of named entities that people detect in the text retrieval field are not the same as the ones that we need for speech synthesis, but I think those approaches could well apply. They are very knowledge-based, and I'm in Apple, and we entertainment media is a big part of our business. So I've spent a good deal of my life dealing with issues like this and finding out, experimenting with ways of detecting them. No matter what approach you take, it's going to be based on human knowledge and a lot of a priori knowledge. So once again, you need to find some way to represent that knowledge so that the text processing part of a synthesizer can make use of it, and then some way to generalize from the cases that you have provided so that it can recognize other cases. For example, an interesting exercise is go to iTunes and type in a few words from a song title, not the whole song title, but a few words of a song that has had many covers. And you'll find all the covers, 120, 160 of them will come up. And each of those entries was entered into a database by some person who worked for a music company some years ago, who had hundreds to do before lunch and typed them just enough for the boss to be able to say, yeah, you're finished. So there are widespread and inconsistent abbreviations in them. It turns out if you have just about any application that needs speech synthesis, then you'll be speaking more text than could have been recorded by a human, a voiceover talent just coming in and recording human speech, which means you'll be speaking a large amount of text, therefore a text from a large database. You could think of Associated Press as a database. And if any database exists that's that large, then it was produced by humans, and the task was tedious, and there'll be quality control problems. In our case, quality control means idiosyncratic variation in how people represent text. So, I'm touching there's overlap. We're going to get back to that. In the case of named entity detection, if you can specify entities in such a way that you can recognize them in text, then the task for speech synthesis is to figure out how to say them in such a way that the named entity is slightly separated for the listener from the speech on either side of it. It turns out that even cases like money amounts I mentioned before, $1.74 billion. If this occurs in a sentence, then you need to not only expand those words, but you need your data structure to keep track that the resultant string of words came from one entity, one named entity. It's not one orthographic item because there's a space in here, but the whole thing needs to be, in some sense, separated from the text around it. See if I can give you an example. We spent over $1.75 billion on this project. Did you hear how I said that? We spent over $1.75 billion on this project. I paused for about 60 milliseconds on each side of that $1.75 billion. Not long enough for any pause detector to detect a pause. But there was a pause there was glottal constriction, there was characteristic lengthening of the material just before the pause, just like you would see in a larger pause, and there was changes in pitch, which we'll talk about shortly about what you need to do. So where I'm going to be heading with this, the theme coming through this, will be that we draw our speech synthesizer architectures as a series of boxes, and that damns us to failure. You'll see things like this. Text comes in, goes through text normalization. Goes into named entity detection. I'm going to talk about more of these boxes. Goes into part of speech. The problem with this serial architecture is that errors propagate. So if there's an error here, none of this will recover from it. And information down here can help resolve some ambiguities here. And so what we really need is some kind of architecture where we can do joint inference on the basis of kinds of analyses rather than the serial form. As far as I know, Festival is still serial, am I right? Yeah, yeah.
But not all the boxes just put one string, that'll be lattices and nests, that sort of thing.
Yes, and if you do, that will help you for the immediately following box. But to propagate the ambiguity to postpone decision making as much as possible makes this look more like they become a joint estimation problem. I'm not disagreeing with you, I'm just thinking in terms of. So, we've looked at some examples of what you need to do for text normalization. We've looked at named entity detection. We've not talked much about how to do it, but certainly why you need to do it. We've talked about some of the problems with part of speech. Let's talk about pronunciation. The task here is you've got a word, you know the letters, you know that you want to treat it as a single token and a single word. How do you figure out what the phonemes are? Well, the old approach used to be to make rules or use machine learning systems to make their own rules. And it's really, really hard to do that and get the words right. You know, these things have something like a 0.96 probability of getting things right. Well, if you have a 10-word sentence, what's 0.96 to the power of 10? It's 0.4, 0.5, yeah, something like that, which means 60% of the sentences will have at least one error in them. You know, it's amazing speech synthesis works at all. The approach that we took at Apple is, others have taken this as well now, is be knowledge-based. So we start off with a large dictionary. In our case, we have about 120,000 words in the dictionary, and each word has got the phoneme strings associated with it for each of its possible pronunciations, tagged with part of speech and a little bit of semantic information. So the first line of defense in figuring out how to pronounce a word is look it up in the dictionary. Trouble is, native speakers of any language are creative, and so we create new words as we go, neologisms. There are things like file saver, timeshare, keep coming up with words that aren't in the dictionary. So we need to then deal with what happens if there isn't a hit in the dictionary. So we have a few lines of defense for that. The first line of defense is can we concatenate two words that are in the dictionary to make this word? And so that works well for things like timeshare and file saver, but it doesn't work for many words. For those words where it does work, sometimes you get wrong analyses where there's more than one way to say a word. I won't write this up. Well, first of all, let's let you think about it. Well, I was reading out, having a synthesizer reading out a sentence, and in the middle of it talked about bull's head. Tick, 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 tick. What sounded a lot like, and in fact was, right, okay, and we had it saying things like, it's all a crap's hoot. Figuring out whether we can agglomerate words in the dictionary to make new words is one way to generalize from knowledge that we know to knowledge that we don't know. But that generalization also needs to be based on knowledge of what kinds of patterns are more likely. So we could say that if a word can be composed, a new neologism can be composed into two words in the dictionary multiple ways, which combination of parts of speech do we like, and do we prefer plurals or singulars on the left? It turns out, so we have a bunch of rules like that that we've accumulated by pain, and they break sometimes as well. There's more work to be done on that. But there are some cases where we just can't accumulate words in the dictionary to make a word. So then we do morphological decomposition. That is, have here a folder. I can tell by its folderness, its very nature of being a folder. Right? Folderness. You won't find that in any dictionary. But you can tell what it means because it has the N-E-S-S ending and it has a known root. So we then, so do we have any known affixes, known suffixes or known prefixes that we can strip off and then look up what's left in the dictionary? And we do that recursively and build up a structure of those till eventually we find hits in the dictionary for the roots and then take the phoneme sequence of the root and do surgery on the phoneme sequence to change it to add the suffixes. So, for example, if the word prettily were not in the dictionary, it is, but if it weren't there, we could say, ILY, that looks like an adverb ending from what would be underlyingly an adjective. Let's take off the ILY and replace it with a Y. That would make PRETTY. Look that up in the dictionary. Whoa, we have a hit. So we pull that out of the dictionary, then we look at the phonemes and we see that it indeed ends in an E, pretty, an unstressed E. So we strip that off and put an ly on there and we come up with prettily and we're done. And that covers another large subset of the cases that we weren't dealing with before, but not all of them. So if that doesn't work, then we throw up our hands and give up and use letter to sound rules that have been trained with machine learning. We use a CART approach to letter to sound rules. Turns out it's not great, but neither is any other approach that I've seen. It seems that no matter what approach you use, the important thing is to make sure that all the training data that you train it on is carefully checked by hand to make sure it's not being trained on errors, particularly in dictionary transcriptions, not being trained on inconsistently transcribed data. And if you do that, then you can get whatever approach you take to work much better. We found we needed two different sets of letter to sound rules, one trained just on names and a different set trained on everything else. That's because names are not pronounced according to the pronunciation rules of the rest of language. Let me give you an example. Some examples. I still don't know what pronunciation is meant by that. Doherty, Doherty, I've heard both. Here's a great name. If you know this name, or know somebody with this name, do not say anything. Oops. Who has not seen that name? Good. How should that be pronounced? What might be a reasonable pronunciation of that name? Migo, yeah. Yeah, that's possible. Any others? Mega, yeah. The owner of that name is quite adamant. It's pronounced Mar. Right. By using a machine learning technique like CART, you can generalize from cases that are new names. Thank you. Other new names that haven't been seen before. It turns out that the mapping between letters to phonemes in names depends on the language origin of the name. So if you look at this sequence in Abe Lincoln, it's pronounced one way, but in a name like Watanabe, it's pronounced quite differently. There have been a number of approaches that have been developed to try to analyze the letter string to classify what linguistic group does it look like this name came from, and then switch in a special set of letter to sound rules or a trained subsystem for names from that origin. Works moderately well, but makes errors. For example, I was working with a speech synthesizer a few years ago on an application to read out the names in telephone list directories given the telephone number, reverse directory assistance. You know, normally for directory assistance you call an operator and say, what's Jim Jones's phone number? But you can also do a reverse search, which has a lot of important applications: law enforcement, pizza delivery, identity theft and identity recovery, and so on. So in this application, we had this corpus, so I'll pull out the names from the name field of the corpus and put them through a name pronunciation subsystem. And one of the names was this. Which it pronounced as Gorham Health Services. Because I had sent this to a name pronunciation subsystem, it didn't have access to knowing that this actually wasn't a name. It believed that it was a name, and it made a very good and correct guess about how to pronounce this, Gorham, or a very reasonable guess. It figured out how this would be pronounced, and it looked at the letter sequence here and thought this looked like a perfectly plausible Spanish name, and so pronounced it as such. The issue here is some sequences of letters will give you unambiguous recognition of the linguistic origin of a name. Others are somewhat less informative and or can be misleading. And I did some work, quite a bit of work on this, because I had to figure out what's the best approach for us to take. And we ended up going back to the CART rules, classification and regression trees, trained on a window of 7 letters with no annotation of the ethnic origin of a name, simply giving it, about 65,000 names and the corresponding phoneme sequences, and having it look at each letter plus or minus 3 letters and figure out the correct set of decisions to ask about each letter to figure out what phoneme should that letter match to. And it caught largely, you know, all the testing that I've been able to do and we've been able to do, it caught the statistically representable generalities about names from different groups and how they would be pronounced in English. So this is kind of learnable as an emergent property. And this approach, I think, does just as well, because if you take the 2-stage approach that I described, that others have experimented with and investigated in the past, of first identifying the linguistic origin of the name and then doing letter to sound rules for that name, you have 2 places where you can make an error. You get the wrong linguistic origin for the name, and independently, you can get the letter to sound correspondences wrong. In fact, you're more likely to get them wrong, I think, because you have a smaller set of data to train each of those sets of letter to sound rules on. Make sense? Yeah. All right. Play a mind game with me. Suppose we can get the text normalization right, the name identity detection right, the part of speech right, the pronunciation right, the pronunciation of names right. Are we done? No, because now we've got to figure out the prosody. Actually, before we talk about prosody, let me just talk a bit about phonemes, because that's part of pronunciation. For pronunciation, we need to map from the letters to figure out what are the phonemes that need to be strung together to pronounce this word. That means you need to have a set of phonemes. And most work in speech synthesis has adopted the sets of phonemes that have worked well in speech recognition. But that has led to some problems because it conflates phonology with phonetics. Anybody here got a linguistics background? Anybody here not got a linguistics background and not know, or the theoretical background of what I just said then? Okay, cool. Let me describe. It's not that complicated. The phonemes of the language are the sounds, the small inventory of sounds. Most languages have about 25 to 50 and usually around 40. The sounds, the vowel and consonant sounds that make up all the words of that language. In most languages, they correspond fairly closely to the alphabet, not so much in English and not at all in the pictograph languages, right? Chinese, Japanese. There are some problems with phonemes, and that is two words are considered to you consider a sound to be a phoneme if you can come up with two words that differ only by that phoneme. So we determined that p and b are different phonemes in English because pig and big are different words. It's that simple. It's tedious, but it's simple. And that's how linguists approach coming up with a phoneme set for a new language. But when we start synthesizing, we notice that you need more variants of the phonemes. For example, the T in Tom is quite different from the T in trough, which is different from the T in water, which is quite different again from the T in hot. And so you might be tempted to say, well, really, there are 4 different T phonemes. And that's what is actually, I think, necessary in the case of speech recognition, because they're quite different acoustic signals, so you shouldn't be modeling them. I guess with Gaussian mixtures you can kind of get at it, but most recognizers will have a larger set of phonemes than phonologists would describe for English. Recognizers usually for English have at least 50, right? 53, 55. And those will add to the traditional inventory that a phonics teacher would tell you, the extra ones that you need to represent different sounds. They will be for variants of T, in some cases voiced H versus voiceless H. Stop me if I say anything that you're not comfortable with. And roticized versions of the vowels, like the O in hot is different from or in, I don't know, order. And so there will be, that's kind of because in a word like order, a phonologist would say the phonemes are, I'll use one of the phoneme sets, or, d, I could do this in IPA as well, doesn't matter. Whatever phonemes inventory transcription scheme we use, the point is these would be transcribed as, this word would be transcribed as 5 different phonemes. An easy case because there's a one-to-one mapping between the phonography and the phonetics. But if you look at the acoustic signal, there is no way that you can divide these two up and figure out where does this stop and where does this start. The gesture of the r in the speaker goes all the way through the or. And similarly, there's no way that you can separate out these. The and the r are completely overlapped to make a kind of an sound. Yes?
So I was just wondering if you could say something
Yep. In 1 minute, you'll be totally clear on that. So phonemes are the sounds that distinguish between words in a language. Allophones are the different ways that a particular phoneme might be expressed in different contexts. Allophones and phones, I think, are two different ways of describing the same thing. Linguists say allophones, and generally speech technologists will talk about phones. So when hidden Markov models usually described as phones and triphone sequences. So allophones are the variants. In the case of T that I mentioned before, I had a released T, that's a T with a closure, a build-up of pressure behind the tongue, and then a release and a burst of air in something like tom, T, top. I had a T that overlaps with a R in trough. It's almost like a ch sound, trough, right? If it occurs between two vowels and the second vowel is stressed, it becomes what we call a tap. That is, the tongue, is the mouth on this side, as the air rushes through the mouth, the tongue wanders up to near where it would be for a nice, clearly articulated T, then relaxes. The air rushing through that constricted space creates an area of negative Bernoulli pressure, relatively lower pressure, which pulls the soft tissue of the relaxed tongue up all the way to touch the top of the mouth, the alveolar ridge just behind the teeth, which builds up pressure under there, which makes it fly away again, and you get this kind of just quick tap, water, water, right? Ura, ura. Acoustically, nothing like any of the other two T's. And if it's at the end of a word or a morpheme, then in American English and somewhat in other Englishes, it's replaced with a glottal stop, hot. There's no release at all. The way an articulatory phonetician would describe it is that when we articulate a clear T, like attack in attack, at the end of the first syllable, the tongue comes up and clearly hits the top of the mouth, and the larynx constricts to make a glottal stop. Then the larynx releases and the tongue releases. The larynx releases just before the tongue, and that's a built-up of pressure, which you then get the sound of attack. Right. In the case of a word final T, these both happen, but there's no release because there's no vowel coming after it. After it, tongue comes away, and then the glottis opens. So hot, hot. Most people, if they say hot, American English speakers, can have some sense that my tongue did kind of drift up to the alveolar ridge, but they can feel that the constriction's in the throat. It's not true. Here's a nice pair to illustrate that. Oops. When police officers work at night, they're paid on a different pay scale. Then when they go into the chemistry lab, they play with these. Can somebody, a native speaker of American English, please read these out?
Nitrates, nitrates.
Yeah. You hear the difference? Nitrates, nitrates. The reason for that difference is this is at the end of a morpheme and at the end of a word, and so it gets that glottalization. Here, the syllable boundary is here, so this is really a tr sound here, nitrates. Okay. So, issues in speech synthesis regarding phonemes are: what is the phoneme set? What belongs in the dictionary? And how do you generate the allophonic variation that you need to generate real speech like this from the phoneme sequence? It's an analogous problem to, given the orthography, how do you figure out the phonemes? Once you've got the phonemes, how do you map from those to the allophones? One approach taken by some of the commercial synthesizers is to not have a phoneme set, or actually to claim to have a phoneme set, but actually have the allophones right up in the dictionary. This means that if the speech synthesis is being used by real application developers in real applications, and those application developers need to customize some pronunciations, they need to understand allophonic variation. Thank you. They need to understand which allophones to use. They'll see that this synthesizer's got 4 T's and 15 vowels that I'd never heard of before, and which one of these should I use? And so I think there's an issue here that's analogous to the computer science architecture question of what goes into my data structures and what goes into my algorithms. If you don't separate those out properly, your algorithms will become too complicated. You know, we always want to simplify the algorithms by getting stuff into the knowledge represented in the data structures. So in the case of speech synthesis, if you have what I believe the right division is to have a phoneme set, not an allophone set, in the dictionary and exposed to users, and then have algorithms for mapping from that phoneme sequence to the allophones. How do you do that? Some of it is easy. It's just by context. Let's take one example. I intentionally use this example because it's an embarrassment to me. You know, I'm responsible for speech synthesis at Apple, and so I'm responsible for our phoneme set. And we have, I inherited a phoneme set that I did not change because too many people were depending on it, and it has largely a clear distinction. It's clearly phonological, except I have 2 things in there that should both be one, and they are 2 different forms of schwa, one that we write that way and one that we write that way. A linguist would transcribe this one like that, and this one as a barred I, like that. This is a schwa, an like in the word about. This one is, you would articulate it by saying I, but when we say I, our lips are spread slightly. You unspread the lips, but keep the tongue in the position of the I. So it becomes I. And it's, an example would be what's in roses, the I, here. If you use this one down in here, it sounds awful. If you use this one up here, it sounds awful. It should not be up to the user of a synthesizer when figuring out how do I pronounce my favorite drug name or my technical terms to know and understand this difference. It should be the task of the synthesizer. So in an attempt to somewhat alleviate the problem, no matter what we use, what a user uses, we map them both to the same thing, and then we have rules that figure out from the context which of these 2 allophones of schwa should we use in a particular context. And that does most of the work, but not all, because of prosody. So now it's time to talk about prosody. Prosody is an organizational framework that spans the linear sequence of phonemes and morphemes and words and organizes them into a larger structure. You could represent it as trees, you could represent it as tiers with lines dangling, however you represent it. That's the way the linguistic material is structured. And if you only have the string of phonemes, it's very ambiguous. You can't really understand it. And so we signal for our listeners that structure by the intonation, the pitch, the rhythm, the pausing, the way we say what we say, the amplitude, although that's emergent. And it turns out that this structure affects every part of the speech signal that has yet been analyzed. It affects phoneme choice. For example, I actually have one here for you. this is ambiguous. What's the subject? Well, if I say, the nights that we met, you were awful, then it was the nights of the subject. But if I say, the nights that we, if I say, the nights that we met, you were awful, you is the subject. But if I say, the nights that we met you were awful, then the nights is the subject. Very, very different structure. The different structure, one characteristic of that is where the phrase boundary is. The nights that we met, you were awful, you is the subject of the sentence, versus the nights that we met you were awful. Now, if I say it with a pause like that, it's easy to synthesize. But it turns out that the way people usually say things like this, you're not even aware that there was an ambiguity, and there's no pause, but the location of the boundary changes the allophones that are chosen. So that if the t and the y occur without a phrase boundary between them, they get merged into a kind of a ch sound. The nights that we met you were awful. And if the boundary is here, there is no way you can say this sentence with the boundary here, with you being the subject, and a ch there. The nights that we met, you were awful. You know, it's just not possible to say it in English. It's not part of the language. Anne Cutler did some cool experiments with a set of about 20 sentences like this, where she she recorded people saying one and just cut out that piece of the signal from one and spliced it to the other and played the sentences to people and asked them to paraphrase the sentences to figure out which interpretation they'd made. And 85% of people's judgments, if they'd been responding randomly, it would be 50%. But 85% of them you can predict just by these few milliseconds of acoustic signal. I think I actually recorded myself saying this so that we can look at the spectrogram for that. That woke up, but this hasn't. Do I have that here? Yes, I do. I have no screen here. All right, I'll do it that way. Let's go to the Finder. Ba-boom. Get rid of my wrong backups. And bear with me for a moment. There we go. Oh, cool. And there we go. Oh, yes. Where's Pratt? There we go. You guys know Pratt, right? Anybody not know Pratt? It's a free signal analysis and speech analysis set of tools that you can download from a university in the Netherlands, and it's pretty cool and used by most people in the community now. So let's play these. This is me at home using the internal microphone, so you'll hear fan noise in these recordings. The nights that we met, you were awful. The nights that we met, you were awful. You hear the difference there? The nights that we met, you were awful. The nights that we met, you were awful. So here is the difference. Whoops. It's kind of awkward using it like this. The nights that we met, you were at you. You hear the ch there? And if you look at the spectrogram, I won't go and make this a spectrogram reading class, but you can see there's quite clear frication. There's no release of the T here, whereas there was over here. There's the very high second formant coming in with the overlapping with the T release. And so to get that right, you've got to get the prosody right. Prosody conditions the choice of allophones. It can even condition to some extent the choice of phonemes. Prosody affects voice quality. What do I mean by voice quality? In synthesis, in recognition we don't care so much about voice quality, but in synthesis we do. Voice quality is the settings of the larynx. I've got a larynx in here somewhere that the vocal folds as they come together and oscillate to provide the excitation that goes up into the vocal tract to excite the formants. Have I lost anybody? Okay, cool. So it's not just characterizable by its fundamental frequency. As the vocal folds come together, they close off, causing pressure to build up from underneath, from the subglottal cavities. That pressure eventually builds up such that they open out and air rushes through. The air rushing through causes another one of these negative Bernoulli spaces to cause them to pull together, and they close again. Once they close, then you get the same thing, this repetition of building up, and that's how you get oscillation. Let's look at the waveforms for that. If we look down the larynx, and you could imagine an ideal larynx that only had one vocal fold rather than two, you could characterize it as oscillating more or less in a sine wave. Except that there are two of them and they hit together, which means if you look at the area of the opening, looking down the trachea, it actually, let's do it at the bottom. It reaches a minimum and then looks kind of like this. Make sense? Because they hit each other. The airflow is the derivative of this. Let's see if I can do a derivative right here in front of everybody. Oh, no. The airflow maps with this but becomes skewed because of inertia and momentum in the system. If you did a finite element analysis, you'd be able to monitor that because the air is a bit compressible and so on. So with the airflow, looks more like this. I'm having like a gradual rise. The airflow reaches its peak after the area is starting to close down again. And then when the area completely, the cross-sectional area completely closes, then the airflow stops. So it's kind of steep like that. And the acoustic excitation entering the vocal tract is proportional to the derivative of this. So now I'm going to see if I can do a derivative in real time in front of you guys. I hope I don't embarrass myself too much. There's 0. So the derivative is 0 here, and is 0 here, is at its most positive here, and very negative here. So we get a shape like this. Those of you who have recorded yourselves talking and looked at the waveform in detail will have seen this shape at the end of a schwa and at the beginning of a schwa. Right. Have anybody seen that shape in there? Well, that's why the shape looks like that. The amount of tension, muscular tension in the vocal folds, determines how quickly they close together again. That determines the steepness of this and the change of angle here, which causes, which determines how high, or low in this case, this is. That, because it's sharp, puts a lot more high energy, high frequency energy into the spectrum than if it were smoother. And so as I increase the tension in my vocal folds, the ratio of energy in the higher frequencies, a kilohertz and higher, to the energy around the fundamental frequency changes a lot. And when we stress a syllable, emphasize a syllable, or rather when we give a syllable a pitch accent, we increase the muscular tension because there's a gesture there, and that boosts the high energy in the spectrum. So if you have a speech synthesizer that doesn't model that, the speech will sound kind of bland and cartoon-like and not quite natural. Okay. So prosody influences allophonic choice. It influences the overall shape of the spectrum. It influences, the prosodic structure certainly influences the chunking, and it determines the pitch contour. Pitch is the most salient single characteristic of human speech. Now, maybe amplitude a bit more. If there's somebody in the other room talking, thank you, somebody in the other room talking, and I can hear them, but I can't hear what they're saying. All I hear is the I'm hearing the pitch. It's a very robust part of the signal. Now, it seems to me evolution is pretty good at figuring out where to hide the information. The part that's the most important for people would want to hide in the part or store in the part that's most robustly conveyed, and that's the pitch. So a traditional view of pitch by some speech technologists has been that the pitch and the rhythm are just some kind of layer of naturalness over the real linguistic content, which the linguistic content being the phonemes and the words, which make some kind of add some kind of nice emotional feel and make it sound more pleasant. Turns out that's not the case. The intonation, that is the pitch contour, is as much a linguistic part of the message as the choice of words or the choice of phonemes. If you change the phoneme, you change the word. If you change the pitch, you change the underlying linguistic representation of the sentence. Take, for example, Ronald only introduced Mary to Miranda. Ronald only introduced Mary to Miranda. That means he didn't introduce Mary to anybody else. But if I say Ronald only introduced Mary to Miranda, that means he might have introduced Mary to a lot of people, but to Miranda, Mary's the only person that he introduced. And if I say John only introduced Mary to Miranda, then he didn't really encourage them to get into bed together. The same sequence of words can mean totally different things. That is, if you made a formal semantic representation of the underlying semantic content, you would have a very different representation for the same sequence of words in the same sentence just by changing the intonation. John didn't leave the party because he was drunk. Did John leave the party? No, he was drunk. But if I say John didn't leave the party because he was drunk, that meant he left for some other reason. He did leave the party. You can make a formal representation of the underlying semantic content and reverse the sign on the proposition just by changing the prosody. Some years back in the 90s, the World Cup final was in the Bay Area. Does anybody here long enough to remember that? Morgan, you might have remembered that. Yeah, you were here then. And it came down to being Brazil versus Italy, as it often does. And that was the final match was down at Stanford. And it was 0-0 all through the game, right up to the end, as it often is with soccer. And eventually, one goal was kicked just about 2 seconds before the end by Brazil, so Brazil won. And there were two priests watching the game, a Brazilian priest and an Italian priest. And at the end of the game, when Brazil won, Italy, I should tell you, had won the World Cup the year before. Right? And so the priest watched Brazil, his country, kick the goal, and he said at the end, God was on our side. And the Italian priest said, God was on our side. Right? You can change the meaning totally by changing the intonation. Once you've got the words, you haven't got enough. Julia Hirschberg was given a kitten, and so on the way home she dropped up by a convenience store to buy a flea collar for the kitten. She got home, and on the flea collar she read the words, "This flea collar could be dangerous for older dogs and cats." She had a young cat. Now, did it mean older dogs and cats, in which case she's fine to use it on a young cat, or did it mean older dogs and cats? She couldn't tell. Once you've got the words and the correct pronunciations and the correct text normalization and the named entity extraction, you still don't have enough. You've got to get the prosody. And a problem in making progress there has been the lack of consensus on how to analyze and represent prosody. A big step forward was made when we came up with a way to transcribe prosody where transcribers would have a high intertranscriber agreement. The system was learnable, and it would represent prosody as categories, so that they could therefore be represented in computational linguistics and text analysis and natural language processing, and yet could be related to the continuously varying parameters of pitch and duration and amplitude and so on. And that transcription system is ToBI. I'm sure several of you have heard of it. Let me walk you through some examples of it. Let's get rid of this guy. And, for those of you who are Mac users, if you hold down the Shift key when you do that, this was put in place just for Steve Jobs. You get demo mode. Ooh. Okay, let's get rid of that. We'll do demo mode again. Hold down the Shift key. It was just so we could show off how beautiful it was. All right. Gosh, this is hard. So let's do. Whoa, that wasn't what I wanted to do. Well, that sorts itself out. We'll do this. Get this down here. Do that. And we'll get rid of soundtrack. Cool. So here's the sentence that I gave you before.
Ronald only introduced Mary to Miranda.
If we look at this, there's a kind of a rise here. This is fundamental frequency extracted by cross correlation of the signal. Time going this way. There's the acoustic signal, and the grey, dirty-looking stuff behind there is the spectrogram. I should have said all that before. I'm sorry. So by following the blue, we can find here's my fundamental frequency. I have a peak there at about 140 hertz, and it jiggles, but in a downward direction, and then has this up-down shape around Miranda.
Miranda.
All right, let's get the M in.
To Miranda.
Okay. This is called a pitch accent. I could say that sentence with essentially what you all agree is the same tune, but with a different word emphasized if I move the emphasis back from Miranda to Mary. So let's see what that looks like. Where are we? There we go. Bring it down to here. And let's get out of here. Cool.
Ronald only introduced Mary to Miranda.
The up-down shape has moved earlier in the sentence. If I show you the other one, this up-down shape here has essentially the same shape, but it's just earlier. If I say introduce, move the pitch to the accented word to introduced, which is up here, cool. There, cool. We see it moves even earlier. Now you don't see the whole up-down movement because there's the bit of voiceless region, the loses its voicing, and the s of introduced. But if you fill in those blanks, you see the same up-down shape. This is a pitch accent, and what we see is that it's characterized by a relatively high peak associated with the accented word, and is moves around in the sentence as we move around which word is accented. The end of the sentence ends low in all cases. Right. So we call this a pitch accent. Because it's high, we call it a high pitch accent. And because it's associated with the accented word, we put a star onto it. So that is, we can characterize that as a high star. I there with a little star after it. Except that it's actually, the pitch doesn't slowly rise up to that peak. The pitch actually reaches a low point just before it and then has an upward swooping shape. And so it's really got a low just before it, so that accent is really what we call a bitonal accent. It's a low plus high star. That is one of the two most common pitch accents that you'll ever have to deal with in English and in many of the Germanic languages. So if we listen to Mary there,
Mary,
you hear the Mary, kind of hear that rising sound?
Mary,
Then that's the low plus high star that we're hearing. If we do that with Miranda, introduced. Let's see if I can get.
Produced.
Look at the in there. Introduced. You hear that rise in there? That's the characteristic sound of a low plus high star. You go home tonight, you listen to the news broadcast, you'll hear those all over the place. News broadcasters put in lots of those because they sound kind of cool and energized and like they care, this is important stuff. Now, there are different ways you can say any sentence, and one alternative way of saying that sentence would be with an accent that's traditionally been described as a fall rise, where pitch falls and then rises up again. That would sound like, actually let me find my recording of that. There we go. Let's just play that here.
Ronald only introduced Mary to Miranda, but he introduced George to lots of people.
So here the way I say Miranda, you can hear that I haven't finished speaking. There's more to come, right? Yes?
Ronald only
Wow.
introduced Mary to Miranda, but he introduced George to lots of people.
Okay. Sorry, I thought I had longer. Cool. Okay. We'll wrap this up then. So if we take a look at that, you'll see that it resolves into, let's get rid of some of these. There it is.
To Miranda.
It comes down, comes up, down like before, but then the duh has quite this big rise in it. If we do the same game that we did before of try to say that sentence with that tune, but shift the accent to Mary rather than Miranda, then we can look at how does this shape get spread out across more material. And it turns out it resolves into two separate parts. It resolves into this rise and fall, and then the rise at the end. So I'll just show you what that looks like with the rise at the end. Bum, 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 bum. Bum, 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 bum. Here we go. There it is, right there. Let's play it all so you can hear it.
Ronald only introduced Mary to Miranda, but he introduced lots of people to George.
All right, so let's play just this part.
Ronald only introduced Mary to Miranda.
What we find is that the peak moved back to Mary, but the final rise stayed final. So a full rise actually turns out, if you analyze it like this, resolves into two clear and separate shapes. One is glued to the right-hand edge of the phrase, to the right-hand boundary, and that's called a boundary tone. And the other one is the pitch accent, and it's exactly the same pitch accent we used before. If you separate them out like this, it turns out that what earlier analyses thought were two different accents are actually both the same accent. What we're talking about here, so we would characterize that one as having a rise at the end. So since it's high at the end, we make it high. Since it's at the end, at the boundary, we use the traditional linguistic transcription of a boundary, which is a percent sign. And since those first utterances were low down at the end, we'd say that these ended in a low final boundary tone. And you can say this sentence varying somewhat how much you rise here. But they will all sound to you like variations of this tone. And if you get it down, saying it with a lower and lower rise, there will come a point where it flips and now it sounds like this one. And you cannot say it in a way that is smoothly in between. Just like you can't say a word that has a phoneme that's ambiguous between P and T. It has to be one or the other. You can't say a vowel that's ambiguous between E and U. People will hear it as one or the other. This categorical perception happens with pitch in lots of ways. This is one of the ways it happens. It means that underlyingly, pitch has a phonology. And so that makes our task for speech synthesis a lot easier, because now we already have this vast literature of approaches to analyze text, to extract categories and discrete categories and symbols from text. So it gives us a way to apply all of those to extract symbols to represent the prosody. And then we can separately within the synthesizer have rules that map from this underlyingly symbolic representation to the continuous variability of duration and pitch. So in speech recognition, the problem is variability. Different people will say the same thing different ways. The same person will say the same thing in different ways, in different contexts. And you want to recognize and transcribe what's the same despite all this variability. So we have awesomely sophisticated algorithms to systematically factor out and throw away that variability. In speech synthesis, we have to do the opposite. We have to explicitly model every aspect of that variability. And the way to do that is by understanding what the prosodic representation should be, generating it from the text, and then using that to drive the acoustic parameters. To get the prosody right, you can't just look at the words. You've got to look at the information content. You've got to look at how it relates to what the listener already knows. In the general case, that's really hard. But in most applications of speech technology, you can have some guess about that, because most applications of speech technology involve a user interaction where you know something about what the user's trying to achieve, and perhaps there's even been a dialogue, in which case we're in great shape, because you know what's just been spoken. So you can figure out which parts of what am I saying now, or what I'm saying now, is new, and how do we mark that with the prosody as being new to help the listener to know why we're saying what we're saying, which parts are old. In the Alex speech synthesizer in OS 10, we analyze the text a paragraph at a time and have a psycholinguistic model in there that tracks the topic structure, building up a model, rather simple model, but it's a model of the listener's set of currently evoked concepts. Currently evoked concepts being those that come from the information content of what's been spoken. As every sentence comes up to be accented or to have its prosody generated, the choice of whether to accent a word or not depends, among other things, on whether this word represents a new concept in the current set of topics in this paragraph, or is a reference back to a concept that's already been introduced. We mark the paragraph structure by putting different boundaries between sentences that span paragraphs than we do between sentences that are within a paragraph. We have a longer pause. We raise the pitch of sentences that start new paragraphs, and then during a paragraph we bring the pitch range down to about the normal pitch range for that person or that particular speaker, and then toward the end of that paragraph we roll the pitch off even lower. Then we raise the pitch again for the next paragraph, so there's an up and down happening. Your homework? Go home and listen to the news. Go to the bar and listen to your friends telling jokes. That's what humans do. I've run out of time, but there's one more thing I want to talk to you about, but it only takes 2 sentences, and that is one of the things we put into Alex that's largely been ignored and I think shouldn't have been in the past is breaths. If you listen to humans, we're breathing in all the time. We have been for, 200 million years? That's the broadest interpretation of we. Ever since there have been lungs, there's been breathing in. It seems to me that nature, evolution, will use every aspect of the signal to help listeners resolve those aspects that are ambiguous. when we breathe in, we put our mouth into the shape of the next word to be spoken. That means the spectrum of the breath intake contains an anticipatory representation of the spectrum of the next vowel. So I'll say easy or awful. Did you hear the difference in the breath? Right. So if you can have a breath sound in there, you're helping the listener to have some more redundancy in the material. If you just say a word at random, how many words are there in our active vocabulary? I don't know, 1 in 500,000 in our passive vocabulary that we recognize, something like that. So if I'm going to guess what word you've said, and I have no knowledge about what you said, if I'm just going to guess, I'll have a 1 in 500,000 chance of being correct. If I am told beforehand what phoneme it starts with, before I've even heard the word, I've reduced the search space by a factor of 40 or 50. So we have breaths in there. People say, well, it sounds nice. I think the reason it sounds nice is that it reduces the cognitive load on the listener when trying to recover the meaning from the acoustic signal. That is why we're doing speech synthesis. Thanks for your time.